So thanks a lot for introduction, Ishil. So I'm Marcelo. I'm coming from Oxford, and this is joint work with Ishil, and I'll be talking about verification of case safety properties. So before I talk about verification of case safety, I want to start by talking about the difference between safety and non-safety and case safety properties. So as you know, safety properties are a class of property that stipulates that nothing bad happens in a run of the program. So in other words, it means that a counterexample of a safety property is going to be one single trace. Now, case safety properties are going to be a generalization of safety properties, and here we are going to stipulate that there is no bad interaction between k traces. So a counterexample in this case is not going to be a single trace, as in a safety property, but it's going to be a set of k traces. So this may sound a little bit confusing, so let's take a look at some examples of case safety properties. So a standard example of a two-safety property is commutativity. So why is commutativity a two-safety property? So commutativity states that, okay, given some function f, we want to show that for all inputs x and y, f of xy is equal to f of yx. Now, commutativity is going to be a two-safety property because a counterexample is going to involve two runs of this function f, right? So the counterexample is going to say that, for example, f of 1, 2 is different than f of 2, 1. Now, commutativity is just an example of a two-safety property. There are many other two-safety properties like determinism, symmetry, antisymmetry, non-interference, and so on and so forth. Now, interestingly, an example of a two-safety property is a familiar notion of transitivity. Now here, what we are doing is we are checking that the predicate f of xy is true, and the x of yz is true, implies that f of xz is true. So note again that transitivity is going to be a three-safety property because we need to run this program f 3 times to obtain a counterexample. So an example of that would be, okay, f of 1, 2 is true, f of 2, 3 is true, but f of 1, 3 is going to be false. So is there such a thing as a four-safety property? In fact, there are four safety properties, and one familiar to you is probably associativity. So if you want to prove associativity, you're going to have a counterexample of 4 runs of the function f. Now, I don't want to go over every case safety property, but I hope that this sort of builds up some intuition that these sort of case safety properties are intuitive and they occur naturally. And we have more examples in the paper. So the goal of our work is to come up with a technique for automatically verifying case safety properties. Now, we believe that this is an important problem because case safety is a key part of functional correctness. And let me give you 2 examples of that. So the first example is comparators. So say you're writing a comparator in your favorite programming language. Let it be from Java to Haskell, right? So you take a comparator and now it needs to behave certain properties to behave correctly. So those properties are, for example, antisymmetry, transitivity, and totality. So another example is if you're coding some MapReduce style program. So in that case, your reducer typically needs to be both commutative and associative. Now that I've given some examples of some case safety properties and some domains where they arise naturally, you may wonder, do programmers actually make mistakes when they are reasoning about case safety? And surprise, surprise, they do make mistakes, and they make mistakes a lot of times. So this is an example of a real comparator from a real Java program. And what we are seeing here is that we have a comparator, and they are going to compare poker hands based on 2 strings. So immediately by looking at this, we sort of see that it's sort of not your trivial comparator, right? So it's sort of hard to see what's happening here. And so it's also not surprising if I tell you either that the program is correct or if it's false, or if it's incorrect, right? So in this case, it's actually buggy, right? So it violates transitivity. But then you start wondering, well, why does it violate transitivity? And it's really not trivial to see why it does that. So this is not an isolated instance, right? So essentially what we discover is that, programmers in their daily life, they actually have a lot of these problems, and you can check many forum posts where programmers are now asking for static analysis tools for checking case safety. And here is a quote of one of them. So this must be a really hard problem if they're demanding for static analysis tools. So in this talk, I'm going to talk about the technique for verifying case safety properties for arbitrary k values. More specifically, it is a form of a new program logic that we call Cartesian OR logic, or in short CHL. And some properties of this logic is that it is sound, it is relatively complete, and furthermore it is easy to automate. So because it's easy to automate, we built a prototype verification tool, which we call Darais, for verifying case safety for Java programs. Now, before I go into the details of CHL, I want to go through some brief background. So there's been some prior work on verification of case safety, mostly exclusively for the verification of two safety properties, particularly in the context of security protocols. Now, in this sort of context, the most widely known two safety property is non-interference. So for those of you unfamiliar with non-interference, essentially you have a function, it receives some public variables, some secret variables, and it's stating that, okay, if you run a program with the same public values, the observable behavior of this program has to be the same. Otherwise, you can essentially infer something about the secrets. So non-interference is going to be a two-safety property because a counterexample is going to involve two runs of this program path. Now, this problem in particular for interference has been studied in the literature, and the solution has been, we are going to reduce to safety to standard safety. So let's take a look at how does it work. So you're given a program. It doesn't really matter what the program is doing. You're just given a program, and you're given a two-safety property. And in this case, it's non-interference or a variation of non-interference. And the first step is we're going to construct a new program from the original one. Now, there are several methods of doing this. The simplest method is called self-composition. And what do we do in self-composition? You take the original program, you create two alpha-reading copies of it, and then you sequentially compose them. So it's very simple. The second step, we are going to put a specification on this new program with assertions based on our property. And now, we are basically already reduced, and we can take this instrumented program and we can pass it to an off-the-shelf verifier and check if it is correct. Now, the key property is that the original program is going to satisfy the two-safety property if and only if the new program is going to be verified. So there are a lot of details to make this technique practical in this methodology. So I'm going to give you some problems that occur once we try to apply it. So the first problem is that verifying the new program can be very difficult. So in particular, if you take self-composition, you typically need to compute exact or very precise post conditions. And this is unfortunately unfeasible if you have loops, recursion, or more complex constructs in your program. Now, if you don't do self-composition, there are other approaches that you can basically build what we call the product program. Now, the problem with that is that there are several strategies of building a product program. So the idea of building a product program is that, okay, we take the two alpha-reading copies, and instead of just sequentially compose them, we are going to sort of, interleave them in some way. But it's not really clear on which way you should interleave them. So if you are naive about it, you can actually cause an exponential blow-up in the size of this new program. So our work, namely Cartesian order logic, is addressing these two issues. And so what is the high-level idea of the CHL? So the high-level idea is that, okay, like previous works, we're also going to reduce case safety verification of case safety to standard safety. Unlike previous approach, we are not going to build one monolithic program and then pass it to an off-the-shelf verifier. Instead, what we're going to do is we're going to say, well, we are going to decompose the correctness proofs, the proof in very small OR triples, and these OR triples are going to be generated in a way that are easy to verify. Now, if you take this approach, CHL actually becomes easy to automate. So you can actually devise verification algorithms that are automatic to verifying case safety properties that perform backtracking search over the proof rules. So let's go a little bit now deeper into the logic. So we know that OR logic, we can show prove the validity of OR triples. Now with Cartesian OR logic, we're going to show the validity of Cartesian OR triples. So what happens in OR logic? So if you take an OR triple, we're essentially saying, well, if you execute program S on some inputs, and this input satisfies P, if S terminates when you run on this input, S terminates when you run on this input X, then the output is going to satisfy the post condition Q. Now, because Cartesian OR logic is reasoning about case safety properties, we actually need to reason about multiple executions of S. So we are going to denote Cartesian OR triples in this notation, and this notation denotes the following. We are going to say, well, we are going to execute S on multiple inputs inputs, which we denote with this vector x, and we are saying, well, if the relationship between the inputs is satisfied by the precondition p, and if the program S terminates on each of them of the inputs, then the vector of outputs that we get, the relationship is also satisfied by the post-condition q. So let's take a look at an example. So here's a Cartesian or triple, and we have a statement, and the statement is z equals x minus y, and the input variables in this case are x and y, and the output variable is z. And essentially, let's look at the precondition, and the precondition is saying, well, in this case we are going to have the two-safety property. We're essentially saying, well, the value of x in the first run is going to be equal to the value of y in the second run, and furthermore, the value of x in the second run is going to be equal to the value of y in the first run. So essentially, this precondition is saying that you are swapping the inputs on the runs. Now, the post-condition is saying, well, the outputs have to be the same, so z1 is equal to z2. So here, we're essentially specifying commutativity. Now, because the statement is essentially a subtraction, and subtraction is not commutative, this actually turns out to be an invalid Cartesian or triple. Now, if you, of course, you change it for an operation which is indeed commutative, you do get a valid Cartesian or triple. Now, let's take a closer look at, since now we know how to specify, how to reason about these Cartesian or triples, how to look at the proof rules. So the proof rules are going to derive judgments of the following form, where is phi and psi are going to denote the pre and the post conditions, and S1 through Sn are going to be essentially programs that do not share state. Now, what is the key level idea? The key idea is, okay, if you take a Cartesian or triple, phi s psi, we are going to say it is valid if you can prove the judgment phi S1 star to Sn psi. And Si is going to be an upper name copy of S. So, what is this S1 O star to Sn? Well, this essentially denotes the space of the set of all programs that are equivalent, semantically equivalent, to the sequential execution from S1 through Sn. So what are the key ideas of the logic? Well, we want to have proof rules that allow the probability of the assertion, but you can pick, as many of these programs as you want. So it's flexible enough to allow you to say, well, I want to pick one equilibrium or another. But furthermore, as I said before, we are not going to really construct explicitly this product program, or this program that can do self-composition. What we are going to do is we are going to discharge auxiliary lemmas in the form of or triples, and these are going to be typically quite small and easy to verify. And this is the key property that allows the technique to scale. So here are some of the rules, and I would love to go through them, one by one and tell you all about them. But unfortunately, I don't have enough time, and I want to be energetic for the rest of the talk and for the rest of the conference. So I'm going to just skip through that, and I'm going to, send you to the details on a piece of paper. And now let's just switch a little bit gears and talk about the automation and how we make this work. So we built a prototype tool for verifying case safety properties for Java programs. We call it Descartes. And the key ideas are that we are going to, it performs backtracking search over the space of proofs. Basically, it's automating reasoning with the logic. Now, because we need to compute loop invariants, that's not a surprise, but we actually need to compute a new form of loop invariants, which we call relational loop invariants. We are using a guess and check procedure to do that. Now, a nice feature of Descartes is that we are able to generate counterexamples, meaning we are able to generate inputs that violate a particular case safety property. So, for example, if you are checking for commutativity, Descartes is able to say, look, it's failing when you put the inputs 1, 2, and 2, 1. Now, we've made the implementation available on GitHub, but I will warn you that it's implemented in Haskell for good or bad. So, how do we check the evaluation of Descartes? So, we're going to check the correctness of custom relational operators in Java. Now, why do we do that? Well, first of all, remember him. The programmer has to manually check, and spend hours doing it, so we want to help him somehow. And second of all, it's because actually these custom relational operators, they involve several properties, several key properties, and they are widespread. You can find them everywhere. Now, the criteria that we use to evaluate Descartes is, well, first of all, can we uncover case safety violations in plugin programs? And is it sufficiently precise, which is sort of normal, right? How high are false positive rates? And third of all, it's how is it practical? Can we actually use the card to verify real Java programs? So in order to answer these questions, I've devised two sets of experiments. So the first set of experiments, we have taken 32 buggy and fixed comparators from Stack Overflow. So there are many others that you can find, but we just select several of them which met certain complexity criteria. In the second experiment, we took around 2,000 lines of code from secret relational operators from mature open source projects in Java. For example, from Apache Storm or Android, etc. So here are some results from the Stack Overflow experiments. I'm just giving you a partial table here. You can find the rest of the table in the paper. And the takeaway message is, well, Descartes is able to correctly identify the violated property in all buggy programs. Furthermore, we're able to get counterexamples for all of those violations, which is pretty cool. I mean, we're just essentially copy-pasting from Stack Overflow and passing it to Descartes, and voila, I wouldn't even know what's happening there. I would have to spend like 5 hours debugging it. And we don't have false positives, and the average runtime is actually quite small. It's about 1.2 seconds. Now, then in our second experiments, where we took around 62 relational operators from popular open source projects, we do have a false positive rate of about 8%. And in this case, interestingly, we're able to find out five buggy operators that were buggy. But because these comparators are a bit more complex, the average running time is about 9 seconds now. So, to conclude, I wanted to make you aware that case safety properties are out there. They need to be verified, and we need like tools that automatically verify case safety. Our solution right now is we have presented CHL, the new program logic for verifying case safety, and we have a prototype tool called Descartes for verifying case safety for Java programs. And currently our evaluation is showing that we can actually use it, and we are getting a low false positive rate. And that's it. Thank you very much. And now questions.
Okay, since Marcelo gave the talk in a record time of 17 minutes, we have a bit more time for questions.
Very nice work. Thanks. So slightly tricky. I don't know how to phrase the question. So one of the things I think about when you say want to check if an operator is, what's the word, transitive, say, right? So one of my favorite examples is lexicographic ordering on lists. So can you give some hint or clue as to what would the the relational loop invariance? Imagine I have some function, a loop, recursive function, whatever it is, that's checking if two lists of, let's just say, integers, it doesn't really matter what, right? Are lexicographically ordered. What kind of loop invariant would I need in order to show that?
All right, that's a great question. So what do we do in that case? So what happens a lot in practice is that people write comparators like lexicographical orders, and typically they are loops with break statements, right? So how do you handle having break statements? So what we did was a specialized logic that essentially transforms these loop with break statements into a loop where you are essentially saying, well, I'm going to put all iterations except the last one in a first loop, and then I'm going to non-automatically choose which way did you exit the loop, right? And then the loop invariant itself, we can use a relational invariant, which is essentially equality on the number of iterations that they have. And that seems to be working quite well. So it really depends on case to case, but in relational invariants that deal with equality between loop bounds and then number of iterations, they seem to be working quite well. So one of the templates that we also have is quantifier for all I between 0 and some constant, in a constancy given by the program, then we know that they are going to be equal to up to that value. So we definitely need to do more work on putting more templates and actually having more powerful inference, but this seems to be working in practice for this type of domains. Thank you.
I have two questions on the evaluation. Did you test the comparator from the beginning?
Yeah.
You did? Okay, great.
Yeah.
And what was the largest K that you guys tested?
Sorry,
The largest K.
The largest?
K. Like a such sensitivity, or commutativity is K equals 2.
Oh, right. So
yeah.
The largest K was of 3. But these comparators they actually need to obey several case safety properties. Right? So comparators need to obey 1 to safety property, and 2 3 safety properties. So, you know, you still have to.
Do you have any idea how it scales as k increases?
That's a good question. The problem of that is that it's not really easy to find, you know, properties, natural properties where k is greater than 4. So if you know of them, just please come forward and I'll be happy to try that too. Thanks a lot.
Any more questions? No. Okay, let's thank the speaker.